Now we're going to consider a problem in which we have to find a force that would generate a specified moment. So the problem statement says that we have to determine the magnitude of the force F that should be applied at the end of the lever such that the force creates a clockwise moment about point O of 15 Newton meters. And we're given this angle theta up here, right here, as 30 degrees. So the question is, what is this force F that's going to give us this clockwise moment around O, which is specified in the problem statement? So this is a vector formulation problem for the moment of a force. And there are multiple ways to do it, but I'm going to show you one that is involving a cross product. So our approach is going to look like this. The first thing we need to do is establish a moment arm. And that's the moment arm that we're going to use in the cross product calculation. Second thing we're going to do is we are going to express the force F, as a Cartesian vector. The third thing we're going to do is we're going to write the cross product. And what we're going to do is compare the cross product we calculate using the moment arm and the Cartesian vector for the force. We're going to compare that with what's given in the problem statement and make the calculation that way. Okay, before we actually go ahead and do the work of these three steps, let's go ahead and look at the figure. So we've got a planar system here. We've got our coordinate system defined, x and y. So that means we've got unit vectors I and j that we're going to use to define these Cartesian vectors. And if we think about how we're going to execute this problem, there's a couple of things we can do. Let me show you one of them. One of the ways we could do this is we could extend the line of action of this force back this way, and we could try to find the perpendicular distance from point O over here to that line of action, and we would call that distance d. We could probably figure that out. It seems certainly doable, but there's a bit of work involved. And what I'd rather show you right now is a vector formulation that allows us a really kind of ordered way to calculate this magnitude of this force F. So let me go ahead and erase that just to tidy up the figure a little bit and show you a different way that we might go about doing this. Okay, so we need to define a moment arm, and I'm going to define a moment arm from O up to this point here where the force is actually applied. So this moment arm is going to be going this way. That's going to be defined by R. That's the moment arm we're looking for. So let's go ahead and do step one and see if we can figure out what that moment arm is. Okay. So step one, the moment arm. When we come across a problem like this where we've got a structural member that has some interesting geometry to it, sometimes the most direct path to finding this vector R is to go ahead and just make it something that follows the path of the structure itself. So what I'm going to do is propose to you two vectors that we can use to define R, and I'm going to draw these vectors in red. The first one is a vector from O up to this elbow, and the second one is a vector from that elbow up to the point of interest. And so just to be clear here, let me call this one R1, and then let me call the other one R2. And both of those vectors can be determined from the dimensions that are shown on the figure and the angles. So let me go ahead and write R1 here in red. R1 is going to have a length of 0.3. That's going to be measured in meters. And then we're going to have, with that, cosine of 60 degrees in the I direction plus sine 60 degrees in the j direction. And then R2 is going to be 50 millimeters. That's 0.05 meters. And that's going to be all in the j direction. Okay, so just to be explicit here, these are both measured with units of meters. So then, if we're going to write R, the vector we're looking for, as the summation of R1 plus R2, we can go ahead and do that. And if we make the calculation according to what we've got written in red there, it turns out that we get something like this. 0.15 in the I plus 0.31 in the J, and that has units of meters. So there is our moment arm R, measured from O to the point of application of the force. Now that we have that, we can go on and do step 2, where we express the force as a Cartesian vector. Okay, so here's step 2. We're going to express the force. So our Cartesian vector for force is going to have a magnitude, F, and then it's going to have a unit vector, which indicates its direction. In this case, we're told that the angle was 30 degrees, so we would write this as cosine of 30 in the I direction plus sine of 30 in the J direction, and this thing is going to have units of newtons. So that was easy enough to express the force in that way. So all that remains now is to interpret the cross product part of this. Let me start by writing a moment around point O. That is going to be a vector. It's going to be written as R crossed with F. And we know what we're looking for is for this to come up to be 15 in the K direction. It's going to have units of Newton meters, and because we're told in the problem statement that it's going to be a clockwise moment, we know that for our right-handed coordinate system, clockwise is going to be a negative moment around the k-axis. So let me go back to the coordinate system quickly. We've got this right-handed system, so we're going to be measuring positive directions for moments in the counterclockwise direction, and that means that since we're looking for a clockwise moment, we're going to use the negative sign there. It's going to be minus 15. So now all we have to do is insert what we already know for R and F, make the calculation, see how it goes. So let me go ahead and write this out explicitly. So R is going to be 0.15 in the I plus 0.31 in the J. We're going to cross that with the magnitude, which is F, and then we have the cosine of 30 in the I plus sine 30 in the J. Okay, now I've temporarily dropped the units off of those two things just to save a little space, but certainly R has units of meters, and the force is going to have units of newtons. Okay, so since F over here is a scalar, this F right here is a scalar magnitude. I'm going to pull that out to the front of the calculation just to save some space and make it clear, and then I'm going to go ahead and do the cross product with the I's and J components. So what we get here is F, and then it's going to be 0.15 times, let's see, sine of 30, and that's going to be a positive K, and then we're going to get a J crossed with an I is going to be a minus K, so I'm just going to go ahead and write this as minus 0.31 times cosine of 30 K, just like that. And when we add that all up, we get F times minus 0.193 K. All right? So clearly we're getting something in the negative K direction. We know what this ought to be equal to is minus 15 in the K direction. So clearly all we have to do is equate this with this. And if we do that, we are able to go ahead and write F is equal to minus 15 over minus 0.193, and this just turns out to be 77.7, and that has units of newtons. And there's your solution for F. Let's review what we did here. We are trying to find the force F such that it produces a certain moment around point O. So the way we did this was we defined a moment arm, which is the vector drawn in blue, and we did it as the summation of two other position vectors, R1 and R2. And so we define this moment arm R, and then we use it After defining f as a Cartesian vector, we use it in step 3 in a cross product kind of calculation, and ultimately we end up with our solution, which is that the magnitude of f is 77.7